Okay, the first even was 66. Part A is the force as a function of x is 6x squared minus 6x. Part B, the positions where we are in equilibrium are at 0 meters and 1 meter. And part C, the 0 meter position is a stable equilibrium position, and the 1 meter position is unstable. Number 68. Okay, the positions where we're in equilibrium are at 0 meters, positive 2 meters, and negative 2 meters. At 0 meters, that is a stable equilibrium point. You're on a minimum on your graph. At positive 2 meters, that's an unstable equilibrium point. You're at a maximum on the graph. And at negative 2 meters, that's also an unstable equilibrium position, and you're at a maximum on the graph. And the last question, number 70. In part A, for positive values of x, the potential energy will decrease as the position increases. In part B, the potential energy function is 4 divided by x squared. And in part C, when you graph that, we're only with positive values of x, so that means you're only in the first quadrant. You're going to get a hyperbola in the first quadrant. You know what a hyperbola looks like, right? Where it's asymptotic towards both the x and the y-axes. There is no y-intercept. All right, anything you want to go over? Jerry? Yes. All right, so in question 69, it says that the potential energy of a 4 kilogram object is given by this potential energy function, which is, hold on a second, let me get my camera straightened out. There we go. Which is equal to 3x squared minus x cubed for x values less than or equal to 3, and the potential energy is equal to 0 when x is greater than or equal to 3. Now, in part A, at what positions is this object in equilibrium? So remember that when you are in equilibrium, that means that the force as a function of position would be 0. So the first thing you're going to do is you're going to figure out what is the force function. What is the force? To get the force as a function of position, you do the negative derivative of the potential energy with respect to position. So that means I'm going to take the negative derivative of 3x squared minus x cubed with respect to x. And this is when x is less than or equal to 3 meters. So let's go ahead and take that derivative. The derivative of 3x squared with respect to x is 6x. The derivative of negative x cubed is negative 3x squared. Now I'm going to negate that. So that gives me negative 6x plus 3x squared as my force function. Now what I need to do is I need to figure out at what positions this equals 0. So that means I'm going to set it equal to 0 and solve. So if I factor out an x, I have negative 6 plus 3x. So that means x is either equal to 0 or negative 6 plus 3x is equal to 0. So 3x would equal positive 6, or x is positive 2 meters. So these are two positions where I have equilibrium And since the potential energy is equal to 0 for all values of x greater than or equal to 3 meters, that means you're also in equilibrium at 3 meters and greater. So those are your positions when you are in equilibrium. Oh, 1 second, something's up here with the meat. Something up. Where's the settings for this? When they update Google Meet, it says if the call is empty, they're just going to end it. There we go. Okay. So back to this. We are in equilibrium at 0 meters, positive 2 meters, and for all values of x greater than or equal to 3 meters. Now in part B, it says, sketch that. The potential energy function versus x. All right, so let's sketch it. This is the potential energy as a function of position, and here is my position in meters. So if I were to graph potential energy is equal to 0 for all values of 3 or higher, that means when I get to 3 meters right here, from then on, my potential energy better be a value of 0 joules, horizontal line at 0. Now, for all values less than or equal to 3, I need to graph this. And that's not so hard to graph. You can graph it on your graphing calculator if you want to see what that curve is going to look like. What I did was I evaluated it at my equilibrium positions. I know that if I plug in 3 meters, I'm going to get a value of 0 for the potential energy. I know that when I plug in a value of 2 meters into this, at 2 meters, I get a potential energy equal to 4 joules. So this is potential energy in joules. So that would be at a value of 4 when I'm at 2 meters. And then when I plug in 1 meter, if I wanted to plug in 1 meter, I'll end up being at 2 joules. And then at 0 meters, when I plug in 0, I get 0 joules, and so forth. So it kind of looks like this. Something like that. So now they want to know in part C, what's the stability of these equilibriums for all those values of x? Okay, so if I look at this value, at x equals 0, do you see how I'm at a minimum on the graph? That implies that that is stable equilibrium. The graph right here is concave up. Concave up implies stable equilibrium. The 2 meter position is a point of equilibrium. Notice the graph right here is concave down. So at x equals 2 meters, that implies that we are in an unstable equilibrium position. The graph is concave down. Then for all values of 3 or more, do you see how that graph is flat? It's neither concave up, nor is it concave down. That means this is neutral equilibrium. Okay? Then in part D, it says, if the total energy of the particle is 12 joules, what is its speed at 2 meters? Well, remember that total energy is made up of kinetic and potential energy. They're telling you that the total energy is 12 joules. And I know that when I am at 2 meters, I can evaluate my potential energy is 4 joules. So that means I have 8 joules of kinetic energy. Now that I have 8 joules of kinetic energy, I can get my speed. because kinetic energy is 1/2 mv squared. So 8 joules would be 1/2 of the mass given in this question, which is 4 kilograms, times that speed squared. So if you solve that for the speed, you're going to get 2.00 meters per second. And that's how that's done. Okay? Anything else you would like to ask about on this assignment? That was question 69. No? Yes, Sherry? Yeah? Let's look at question 67. So 67 says that the potential energy of an object is given by 8x squared minus x to the 4th power. All right, so the potential energy as a function of position is 8x squared minus x to the 4th power. And it then says, determine the force on this object in part A. So what is that force as a function of position? To get the force, you do the negative derivative of that potential energy with respect to position, which means I'm going to do the negative derivative of 8x squared minus x to the 4th power with respect to the position. So that means let's take the derivative of 8x squared. That would be 16x. The derivative of x to the 4th is 4x cubed. Now I'm going to negate that whole thing to get my force function. So this would be negative 16x plus 4x cubed for my force as a function of position. Now in part B, it says, at what positions are we in equilibrium? Well, remember, when you are at equilibrium, that net force must equal 0. So let's figure out at what values of x this is equal to 0. I'm going to factor out an x. So either x is equal to 0 or negative 16 plus 4x squared is equal to 0. So 4x squared would be 16. So x squared is 4. So x can be either positive or negative 2 meters or 0 meters. Then in part C, which of these equilibrium positions are stable and which is unstable? Okay. To determine stability, you have to figure out whether the potential energy graph is concave up or concave down. And the way you do that is by looking at the second derivative of the potential energy function and determining whether it's positive or negative. So part C, when you're doing the stability, you do the second derivative of the potential energy. Not the negative derivative, just the second derivative, and determine if u of x is positive, negative, or 0 at those equilibrium points. Okay, so let's go ahead and do that. So I know that the first derivative of the potential energy is 16x minus 4x cubed. That's my first derivative. Now get your second derivative. So that would be 16 minus 12x squared. So now we're going to evaluate that at all 3 equilibrium positions. So if I do this second derivative, evaluate it at 0 meters, That would be 16 minus 12 times 0 squared, which is going to give me positive 16. Since it's positive, that means at x equals 0, we have a stable equilibrium position. I don't even care that the number is 16. It's just positive. It is positive, so that is a stable equilibrium point. That's where the graph is concave up. I'm now going to evaluate that at positive 2 meters. So that's 16 minus 12 times positive 2 squared. So that is negative 32 meters. I don't care that it's, or negative 32. I don't care that it's 32. I care that it's negative. That negative tells me that at positive 2 meters, this is an unstable equilibrium position. That's where the graph is concave down. This positive means concave up. This negative means concave down. That's something you're going to learn about in calculus when you're doing the derivative. So the second derivative will help you to determine the concavity of the graph. And then I'm going to evaluate it at negative 2 meters. So 16 minus 12 times negative 2 meters squared. That's also going to give me negative 32. Again, because it is negative, that tells me again the graph here is concave down. And what we know is that when the graph is concave down, that means that is an unstable equilibrium position. So if you did it and you got a value of 0 at that equilibrium position, the second derivative evaluates to 0. What does that mean? Neutral equilibrium. That's right. Okay? So the second derivative of your potential energy function, evaluate the second derivative of that potential energy function at the equilibrium positions, and that will tell you whether you've got concave up, concave down, or no concavity at all, so you can determine stability. All right, anything else you'd like to ask about? No? That's it? Okay, then let's talk about Lab 8. Lab 8 was pushed out to you this morning, so I don't expect that you have read it yet. But let's talk about what you're going to be doing in the lab, and that way you can start collecting data for it today, because you'll have today, you'll have all tomorrow, and then you'll have a little bit of class next Tuesday to work on finishing all the rest of the data collection for Lab 8. And you're going to be working in groups of 3 or 4. There will be 6 groups total to do this lab. Oh, this is not your class. That's okay. Actually, it is your class. I just had the wrong thing up on the screen. There it is. So let me pull up Lab 8, and we'll talk about what you're doing. There's a lot of stuff here in Lab 8. There's going to be a handout, which I need you to read through tonight, and there is a Google Sheet, which one person in the group is going to use theirs and then share it with the rest of the group to use that to edit the data. You are not turning in the Google Sheet to me. You're going to be copying and pasting your data tables and so forth into your lab report. Okay. So let's talk about this lab. The lab is on work and potential energy. And you're going to be using a setup like the 6 stations I have around the room. So there's 1, 2, 3, 4, 1 in the back corner, 5, and 1 in the far back by my filing cabinets. And what you're going to be doing is answering this question in the lab. The purpose of this lab is to determine how the increase in the elastic potential energy compares to the decrease in the gravitational potential energy for a spring that can oscillate. You're never going to get the spring to oscillate, though. You're just going to get it to drop to a particular point. And the first part of this lab, which is the long part, I'm not even going to go over this. This is how you're setting it up. So you're going to want to make sure you look at that carefully so that way tomorrow when you come to class and you have to set it up, because it's going to be torn down by the end of class today, taking it all out, because my Regents kids and the general physics kids in this room have sticky fingers. So stuff will sprout legs and walk. So I don't want anything disappearing. So we're going to break these setups down before the end of class today and tomorrow and next week. We're going to set it up like you can see here, like we have pictures of, or you can take a picture with your Chromebook if you want, so that way you remember how to set this up. And the first part of the lab, which is in step 2, which is written right here, is to determine the spring constant of the spring that you have there using Hooke's law. Okay, so if I were to go to my Google Sheet, which is posted with the lab, you'll see that I've created a data table for you to do this. And it's a big sheet. It's even bigger. You're just working in table 1 to get your data for Hooke's law. You got to get this data first. And what you'll be populating in this, let me make it not quite so big. That's better. We can see that I'm giving you the mass that you're going to hang from the spring. Then the Google Sheet automatically calculated the weight for you of that mass. And you need to get that mass in equilibrium on the bottom of the spring. That means it's not going to be bouncing up or down. You want it to be as still as possible. What you need to do 1, 2, 3, 4, 5 times for that mass is determine how far the spring stretches. So you're going to put the mass on it, let it get to equilibrium, get a measurement. How far did it stretch? Not its total length. I want to know what is the change in the spring length from nothing on it to putting 0.1 kilograms on it. Then it's going to automatically give you the average and the standard deviation. Thank you, Ms. Famosa. We don't have to do any calculations this part of the lab. Then you're going to do it again for 0.2 kilograms. You'll do it again for 0.3 kilograms, 0.5 kilograms, 0.6 kilograms, and so on. Now, you don't have that many masses at your station, but you can add masses together to get the total mass that's there to make this happen. So I think, if I remember right, there's probably like 20, no, there's more than 25. There's 1, 2, 3, 4, 5 trials for each mass, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 masses, 14, 15 masses to do. Okay, so there's a lot of these, but this should go pretty quick. This is not the hard part of the lab. That's pretty quick. Once you've done that, to get the spring constant, you're going to use the summary data table too, which shows the force on the spring versus the average change in the length to determine the spring constant. And your group should remember how to get the spring constant with the force and the average length. Make a graph of that data. Then this is the hard part. And this part, for table 3, is determining how far the mass will fall on that spring when you put it on there. Let me describe what you're going to do here. And you need to be very careful when you do this, because otherwise somebody's going to get hurt. Okay? Notice that for table 3, when I look at this, there are only 2 masses that we're going to do this with. 0.5 kilogram and a full kilogram. That's it. Let me show you how this is done over here. Here I have a spring, and I've got a meter stick, which I can move up and down. I can also move the spring up and down. And for purposes of this lab, I'm going to suggest you move the spring. And I'm going to move the spring so that way I can see the bottom here on my meter stick. And what you need to do for the entire lab is set it and put a clothespin at the position where the bottom of the spring is 0 on your meter stick. That way you know what to subtract every time to figure out the change in the length. Okay? You can't use 0 because 0 is up here in this clamp, and we're not going to move this up and down. So we're just going to set this up. I got to get it eye level, and I'm going to try to mark it something like that. That looks pretty good. Now what I have to do, I'm going to do the half kilogram one because the 1 kilogram one is a little harder. You have to figure out how far this is going to come down just on the first drop. First drop. And somebody in the group is going to have to place a clothespin on this at that drop, at the lowest point. It happens really fast. So you got to kind of, maybe do it once, figure out about where it's going to go. So I'm going to put it on here, hook it on. I'm not letting it go, and then all of a sudden I'm just going to let it go. Now, the mass, when it gets down to the bottom, has a tendency to want to rebound and jump off the spring. So if it jumps off the spring and it falls to the floor and your feet are there, you're going to end up with a broken foot or a broken toe. Okay, so that's why I need you to be very careful. So you're going to attach it, but you see there's space in there, it's not pulling down, and then once you've kind of figured out where it's going to land, you're going to do this 5 times to get 5 change in length positions. You don't care about it rebounding. You got to get it from here to wherever the bottom of that spring was on the first drop. Then do it again. Then do it again. Do it again 5 times. Populate your table for half a kilogram. And then to do a kilogram, you need 2 halves on there, which you're going to try to release at the same time. I don't have 1 kilogram masses for you, so just get them both on there and then let them both go. Okay? You follow what I'm saying? That's the hard part. Okay? Because it takes a bit of practice, and you can put this here so that way you can then measure the distance between the 2 clothespins. Okay? Questions? All right, so what I'm going to do is I'll put the clock on the screen. For purposes of today's class, you can start getting your Hooke's Law data. You've got about, let's say, 5 minutes, because at the end of the 5 minutes, and then you'll have all class tomorrow, so you're just going to come in and get set up right away and go. But I need at 20 after, we have to take these setups down, all apart. And we'll put the equipment on the side over there. Okay? Go ahead and get to work. Break up into groups, 6 groups only.